Hey, welcome to ShaderNet, a graph-based shader code analysis, to accelerate GPU's performance improvement. This is a joint work between Lin Zhao and Arijit Khan, from NTU Singapore, and Rabi from AMD. GPUs are very important, in a diverse range of applications, such as online video games, deep learning algorithms, high-performance computing, interactive visualization, and computer-aided design. From a GPU chip designer's point of view, it is very important to tune their product to achieve optimal performance, in order to seize the market. However, the conventional tuning approach is usually based on the handcrafted keyframes from the limited number of applications. Doing such a process is tedious and time-consuming. More importantly, it usually has limited diversity and coverage of applications and algorithms. Therefore, we hope to find some opportunity to optimize this process from a code analysis perspective. So, we propose ShaderNet. It is the first public available toolkit that adopts advanced graph mining and machine learning techniques for shader code analysis to make the GPU performance tuning process more efficient and effective. Here is our ShaderNet system architecture. It includes 3 layers. The bottom layer is to conduct data storage and conversion. We convert disassembly shader codes into shader graphs. For a game application, we can categorize them into scenes, then subdivide them into frames. Within each frame, there is a large number of shader graphs. Therefore, we can organize the shader graphs as temporal graph snapshots, over different frames and scenes. In the middle layer, we store important machine learning models and analytical information. In the application layer, we currently provide 4 applications. The first application is to view the shader graphs, and the evolution of the shader graph over frames. On the left page, the user is able to view the graphs converted from shader codes, by selecting the game and the scene. They opt to see an integrated graph per frame, where we merge all graphs within that frame as a disjoint graph. Or, the randomly selected 3 sample shader graphs from each frame. On the right page, the user can see the evolution of graph structure properties, such as node and edge count, the cycle, and degree evolution. The user can see how those properties varied over different scenes. Our next application is to cluster the games into groups. These clusters are obtained based on graph structure similarity values from frequent subgraphs, which are mined from those games with the grouping result. We can select the game that is nearest to the centroid as the representative game for that group. Also, given a new application, we can identify what cluster is the most similar with respect to the new games. And given that the GPU is already tuned based on that cluster, we can leverage the existing solution to do a better job. Our third application is to predict the shader efficiency of new games. The pre-trained model is built using random forest, with indented frequent subgraphs from existing games. Now, given a new game, we can firstly identify its frequent subgraphs, then pass them into the model, to check which subgraphs are in low performance. The engineer, who is working on the performance tuning, can focus on the group of low performance shaders. In this way, tuning based on a new game will be more efficient and effective. In this page, once the user selects a game, it displays 2 samples of low performance frequent subgraphs, and 2 high performance subgraphs, with a brief explanation. Our last application is, given a dataset with unknown frame number, we can predict which scene this frame belongs to. This is based on the observation that, the frames within a scene are quite similar, but frames from 2 different scenes are quite different. The user has the option to choose a game and choose one of the frame number, then the system will report which scene it is. We utilize the graph convolutional neural network model to predict its scene group. In addition, we provide the explainability of our prediction result, by showing the nodes that is the highest contribution to the result, We also show that the training and test accuracy plot. For example, in this case, the test accuracy can be up to 90%. This comes to the end of the demo. Thank you for your attention.